feels. Come feel your jollies, our prices are real.
Come to ShopRite's birthday for more low prices. Like 2 liters Right Brand sunflower seed oil, only $44.99. And 2 liters Nami orange squash, just $22.99. Go Wololo with our more low price birthday.
Grade 10s, we need to mark the worksheet that you had for homework. I trust you have all done the worksheet. And I want to have a look at the answers to those questions. All right. Define the following. Moment is a turning effect of a force. Don't confuse moments with momentum. Momentum ending on the M is the amount of movement of an object. The moment ending on a T is the turning effect of a force. Okay, weight is the size of the pulling force of the earth on an object on or near the earth's surface. If an object is in a state of free fall, it is falling with constant acceleration, no opposing frictional forces. Then inertia is the ability of an object to maintain its state of rest or uniform motion. E, terminal velocity. Terminal velocity is a maximum constant velocity. The reason for this maximum constant velocity is that the accelerating force has been cancelled by opposing frictional forces. People, these two, if I had an object in a vacuum and I allowed it to fall due to the influence of gravity. If it was a vacuum, it would go into a state of free fall. If I stood in our atmosphere on a very high building and I dropped an object, it will fall due to gravity, and initially it will go faster, 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 but the acceleration will become less due to the frictional forces that oppose the accelerating effect. And you will end up with a maximum constant velocity. All right. Density, that's an old grade 8 one. It is mass per unit volume. Don't confuse mass and weight. Density, if you go and look at the formula, it is mass divided by volume. So when they ask for a definition, you may not give the formula, but the definition is usually connected to the formula. So mass per unit volume. All right, Archimedes Principle. This is a good one. Archimedes Principle tells us that an object in a fluid, all right, an object in a fluid. Now, the word fluid collectively refers to a liquid or a gas. So an object in a fluid will experience an upthrust. All right? The size of the upthrust is going to equal the weight of the fluid displaced by the body in the fluid. All right. Momentum, here we have momentum. Remember the first one was moment. Momentum is simply the amount of movement. Moment, ending on a T, is the turning effect of a force. Momentum, ending on a M, is the amount of movement. All right. Center of mass is the point in an object or outside of an object through which the weight works vertically downwards. All right. Center of mass is a point inside or outside of an object through which the weight works vertically downwards. All right, question 2. Figure 1.1 shows the apparatus that may be used to compare the strengths of two springs of the same size but made from different materials. All right, you can see from the diagram they've suspended the spring there from a hook. They've got a pointer fixed onto the spring, and here is probably something like a ruler. Here they have a pan into which they place different masses. Explain how the masses produce a force to stretch the spring. Well, the gravity acts on the masses, giving it weight. All right, so due to gravity on the object, the force is then equal to the mass times gravitational acceleration. Okay, explain why this force, like all forces, is a vector quantity. A vector quantity has direction, and the direction of this force weight always goes vertically down. B. Figure 1.2 shows the graphs obtained when two springs are stretched. Use the values from the graphs and determine the spring constant for each spring. State which spring is more difficult to extend. Now, people, to calculate the spring constant, you need to have the size of the force and you divide it by the extension of the spring. That will give you something, so many newtons per millimeter or centimeter, depending on what you are measuring it. So, you would have to go onto your graph, and to get the spring constant for the spring, I would, for example, go like that, and there where it cuts the graph, you go down onto the horizontal axis, and we will see there it has a value of 25. So with a force of 20 Newton, the extension is 25 millimeters. So over here we would have 20 over 25, and that would give me a value of 0.8 Newton per millimeter. So the spring constant is going to be 0.8. The other spring that they have, and I'll work in a different color over here, we need to do in a similar way. And if you would go, I've just used the greatest range because then we have a smaller error acting on it. And it also goes down here onto 25. So the spring constant for the second spring, for spring 2, that one was spring 1. And then spring 2, we are going to have 15 over 25. That will give me a spring constant of 0.6 Newton per millimeter. The reason they say use the values and determine the spring constant for each spring. State which spring is more difficult to extend. Well, spring 1 requires a greater force to extend the spring the same amount. So spring 1 is more difficult to stretch, okay, to extend. 2. On the graph of spring 2, mark the point P at the limit of proportionality. Explain your choice of point P. Well, where the graph deviates from the direct proportionality, you could maybe use a ruler to help you. Where are my add-ons? Goodness me. There. No. Oh, goodness me. Okay, my ruler is down here. No, I don't want a table. Over here is my ruler. There. Okay, I can take my ruler and we can try and see if I can get it. There we go. At what point does the graph deviate? It seems to be somewhere over there. You would mark the limit of proportionality and you would label it P. All right. Explain your choice of point P. Beyond 15 Newton, we find that the extension is more than what you would expect. Comes 2 marks. 1 mark would be for showing point P on the graph, all right? And the other one would be for explaining that the extension beyond the elastic limit is greater than what you would expect for that spring. 3, use the graphs to find the difference in the extensions of the 2 springs when a force of 15 Newton is applied to each one. Well, spring 2, we know at 15 Newton, it extended 25 millimeters. So we need to go and have a look at spring 1 over here on 15 Newton. Over there, it seems to be about 18 or 19 millimeters. I've not worked all that perfectly accurate. So let's say spring 1 extends 19 millimeters. So the difference in the extension is going to be 25 minus 19. If you had 18 there, it's acceptable. Would give me, in this case, 6. If you had 18, you would get 7 millimeters as an answer. That is perfectly acceptable because one will refer back to your graph. That is also a reason why you need to show your working on the graph. All right. Number 3. A small paper box is falling vertically through still air. Well, paper and air, there's lots of friction. Eventually, we've got a terminal velocity is reached. Now, what does terminal velocity mean? We did it in the definitions. It's a maximum constant velocity because the accelerating force has been cancelled by frictional forces. All right, so this small paper box is falling with a maximum constant velocity. Explain the motion of the box from the start of the fall until the moment just before it hits the ground in terms of the forces acting on it. So, initially, when it starts falling, we have gravitational acceleration causing it to fall faster and faster. But at a certain point, the frictional forces will cancel cancel, oh, sorry. The force due to gravity. In other words, there is no resulting force acting on the object, and it will fall with a constant velocity. Okay. Discuss any differences if the box was allowed to fall in a vacuum. Well, if it was falling in a vacuum, there will be no friction acting on that box. So it would simply fall with constant acceleration, which is going to equal to gravitational acceleration. So it is going to go faster and faster and faster. All right. Number 4, in the year 2525, 2 teenagers from different planets, A and B, exchanged physical information about themselves and the planet they live on. Teenager A has a mass of 50 kilograms, weight is 250, gravitational field strength given as 5. Oh, you have to fill in the 250. They give you gravitational field strength. Let's just orientate this right. Let's say you on Earth have a mass of 50 kilograms. What does that mean in terms of your weight? Well, to get weight, we multiply with 10, because 10 is the effect of the gravitational field pulling on us. All right. So here on Earth, we would have 10, and I would have my mass in kilogram, so my weight would be 500 Newton. All right. So, teenager on planet A has a mass of 50. Gravitational acceleration is not 10 but 5, so it will be 250 his weight. Teenager on planet B, here they tell us his weight, and they give us the strength of the gravitational field. Well, to go from, if I have a weight of, not 600 Newton, sorry, of 500 Newton, to go back to my mass, I would have to divide with a factor caused by the gravitational field. So in this case, we will get 600 divided by 20, and that would give me 30 kilograms. All right. B1, state the SI units of mass and weight. Mass is in kilogram, small letter K, small letter G. Weight is in Newton, capital letter N. Describe the difference between mass and weight. Well, basically, it is the definition. Mass is the amount of matter in your body. If I go to the moon, I don't lose an arm and a leg. All right, the amount of matter is the same, although on the moon my weight is going to be less. All right, so what is weight? Well, the weight is the size of the pulling force of the Earth or the planet, all right, on an object on or near the Earth's surface. All right, it's an old one. I'm not going to write it out. Question 5, figure 1.1 shows a cube with sides 5 centimeters lowered into a container of water until it is completely submerged. Gravitational acceleration causes a force of 10 Newton per kilogram. Determine the volume of the cube. Well, they tell us the sides are each 5 centimeters. To get volume, we need length times breadth times height, or side times side if we have a cube. So it's 5 times 5 times 5. All right? But this is in centimeters. So my answer is 25 centimeters cubed. But over here, what do they want us to do? They are looking for the answer in cubic meter. Now, you can either convert directly, if you know how, all right? To go from cubic centimeters to cubic meters, you will move 6 places to the left. In other words, if your answer is 25, you will go 1, 2, 3, 4, 5, 6. There's my comma. So the answer over here should be 0.000025. If that is too difficult, go and convert centimeters into meters. Okay, we know there are 100 centimeters in a meter, so 5 centimeters will be 0.05 times 0.05 times 0.05, and you should get the same answer. Calculate the mass of water displaced by the cube. Oh, gosh, have I got one wrong? It seems like my memorandum has got... Oh, I have a problem here. Yes, the answer must be 125. All right, so 6 places for 125. Let me quickly correct that. Let's just quickly go back over here. All right, I'm going to do it in green. Over here we have 5 times 5 is 25, times 5 is 125 centimeters cubed. So it's still 6 places. All right, so we have 125. We must go 6 places. 1, 2, 3, 4, 5, 6 places. There's my comma. 1, 2, 3 zeros. So over here, my answer must be 0.123125 meters cubed. Okay, are you with me? People, 5 times 5 times 5 is 125. Don't let the error mix you up. Okay, so calculate the mass of water displaced by the cube if the density of the water is 1,000 kilograms per cubic meter. We must calculate the mass. Remember, density is mass over volume. We've got the volume over there. So we've got the density. We can find the mass. So mass is equal to density times volume. The density is given as 1,000 kilogram per cubic meter, and we have to multiply it with our 125 cubic meters. The answer that we get is 0.125 kilograms. Please remember, if you did make a mistake, let's say for argument's sake, I made a mistake over there, I would lose that mark, all right, because there's a mistake in that part. But if you did all of this correctly, they would mark it error carried forward. All right. And you would get both of your marks over there. Okay, calculate the upthrust on the cube due to the liquid. Well, the upthrust is equal to the weight of the liquid displaced. From the definition, we've just done it, all right? So what is the weight of the liquid displaced? Well, we've calculated the mass of the displaced liquid. So the weight of the displaced liquid is going to be the mass in kilograms times 10, because gravitational acceleration causes a force of 10 Newton on each kilogram. And that would give us a force of 1.25 Newton. Once again, if you had an error over there, okay, come on, I don't want that. All right. If you had an error over here, then they would mark that error carried forward. If you used it correctly, you would get both marks. That's a very important concept, because sometimes if you do a question and you can't get to the answer of the first one, or even say the second step, just put in any value. You will lose that mark. But if you use that value correctly in the next step, you should get credit for that next step. All right. So, D1, calculate the magnitude of the resultant force on the cube in the water if the weight of the cube in air is 3.5 Newton. Well, what is the resulting weight of that object in the fluid? Remember, the fluid causes an upthrust. Its original weight was 3.5 Newton. The upthrust is 1.25 Newton. You will be left with a resulting weight of 2.25 Newton. State the direction of the resultant force. People, no matter where you are standing, lying on a slope, hanging from a tree, sitting on top of a roof, weight always goes vertically down. There is no other place for weight to go. Question 6. A teacher models the collision between two objects by firing a steel ball of mass 0.4 kilogram at a speed of 5 meters per second. Okay. After the collision, the original ball continues in the same direction with a speed of 3 meters per second. The second ball has a speed of 8 meters per second in the same direction. Use the principle of conservation of momentum to determine the mass of the second ball. Well, the law for conservation of momentum tells me the momentum before a collision or explosion must equal the momentum after a collision or explosion. This means that before the collision between the two objects, we have a steel ball of mass 0.4 kilogram, and it's traveling at a speed of 5 meters per second. The second object is stationary. In other words, the velocity is 0. Remember, momentum is mass times velocity. Anything multiplied by 0 is 0. So the momentum before the collision is going to be the mass 0.4 times the speed 5, all right, plus 0, because there is 0 velocity on the second object. Okay? This is going to equal to the momentum after the collision. What has happened after the collision? They say after the collision, the original ball continues in the same direction with a speed of 3 meters per second. In other words, this is the 0.4 kilogram object is now traveling at 3 meters per second in the same direction. Remember, we haven't indicated direction, but this 0.4 is, or this 5 is actually a positive 5. Now they say after the collision, the original ball continues in the same direction with a speed of 3 meters per second. The second ball has a speed of 8 meters per second. We want to know what is the mass of this ball. So, what do we have? Well, after the collision, we have the 0.4 kilogram object traveling at 3 meters per second. But we also have this stationary object is now traveling at 8 meters per second in the same direction. All right? And now we simply have to solve for m. Okay? So we will end up with, let me have a look over here. I have got 2 is equal to 1.2 plus 8m. That's already slightly more simplified. Then we can take the 1.2 across, so 2 minus 1.2, because if we go across the equal to sign, the sign must change, is going to equal 8m. And if I want to get m alone, then I have to divide by 8. So we will have m is equal to 2 minus 1.2, which is 0.8, divided by 8. And the answer then is equal to 0.1 kilogram. Show that this collision is perfectly elastic. What is the rule for elastic and inelastic collisions? An elastic collision is, for example, if I take a tennis ball and I throw it against the wall and it bounces off the wall. Okay? An inelastic collision, if I had a nice soft lump of wet clay and I took it and I lobbed it against the wall and it just goes and it sticks onto the wall, it changes shape, that's it. That would be inelastic. Okay, so to prove that a collision is elastic, we need to go and have a look at the kinetic energy. Remember, the momentum is always conserved. But if we have an inelastic collision, some of the kinetic energy is converted into other forms. So the kinetic energy is not conserved. So we need to go and find the kinetic energy before and the kinetic energy after. And if they are equal, it will be an elastic collision. If the two kinetic energies, the one before and the one after, is not the same, it will be an inelastic collision. So kinetic energy before the collision is just very simply half mv squared. That's the formula. So the mass is given as 0.4, so half of 0.4 times the speed is 5 meters per second. Remember to square it, okay? You sometimes forget to square it. And your answer is going to be 5 joules. Remember, energy is measured in joules. Okay. After the collision, okay, we have two sets of energy. We have the energy of that object and we have the energy of that object. All right. So the kinetic energy after the collision is going to be half mv squared of this object, all right, plus half mv squared, which is the kinetic energy of that object. And this gives me 0.5 times my mass is 0.4 times the speed is 3. Remember to square it, plus 0.5 times the mass that we had to calculate, 0.1 times the speed is given as 8 meters per second. Remember to square it. Okay. And if you go and work this out, you will find the answer to be 5 joules. In other words, the energy before is going to equal the kinetic energy after the collision. And therefore we can say, yes, this collision is perfectly elastic. Number 7. A meter rule is pivoted at its center of gravity. A weight of 8 Newton is suspended from the rule at a distance of 2 meters from the pivot. Okay, here's our weight. It is a distance of 2 meters from the pivot. The meter rule is held horizontally by means of a stretched spring that is 0.4 meters from the pivot. Okay, here is a stretched spring, 0.4 meter from the pivot. All right, state the principle of moments. Well, moments tells me that if a system is in equilibrium, in other words, balanced, the clockwise moment will equal the anti-clockwise moment. In other words, that moment should then equal that moment. Then the system would be in equilibrium. So, calculate the moment of the 8 Newton weight about the pivot. Well, where am I now? Okay, calculate the moment. So the moment is force times perpendicular distance to pivot, and that is going to be 8 times 0.2, and that gives me a value of 1.6. So 1.6, what is the unit? Well, force is in Newton. Distance, is it in meters or centimeters? It's in meters, all right? So we will have a Newton times a meter, so the unit is a Newton meter. We have to calculate the force exerted on the meter rule by the spring. Well, the object is in a state of equilibrium, because they say it's held horizontally by means of a stretched spring. So there is no resulting movement. So the force exerted on the meter rule by the spring, we would use the principle of clockwise moment is equal to anti-clockwise moment. We've worked out the clockwise moment over there. So for this part, we will say 1.6 must equal the force times the perpendicular distance to pivot on the other side. We are looking for this force. That distance is 0.4. So F is going to be 1.6 divided by 0.4, and that will give us 4 Newton. Now, if the spring had an unstretched length of 10 centimeters, when a force of 2 Newton is used to stretch the spring, its length becomes 11.5. Okay, just before we go any further, you need to read this clearly. A 2 Newton force stretches the spring. It originally was 10 centimeters, so the extension is going to be 11.5 minus 10. It's going to make it extend 1.5 centimeters if you have a 2 Newton force. So, if you have 2 Newton and it's going to make the spring extend 1.5 centimeters, calculate the force needed to give the spring a length of 13. Lots of catches. What's the extension? 13 minus 10 is 3. So over here, we want to know what force will cause an extension of 3 centimeter. And it is very simply 3 divided by 1.5 times 2, and that will be 4 Newton. All right. I hope it is clear. If you have any queries, we'll have a Zoom lesson next week, and we can discuss it then, or you can just WhatsApp me. You can just let me know. All right. Okay. Thank you, grade 10s.
is in constant motion. Everything and everyone is moving, and so is GoTV's unstoppable entertainment. When unlikely paths cross, love blossoms, even for the most vulnerable. To some, time has proven to be no factor. All that matters is surviving the trials and tribulations. When you act fast, you become invincible to many. We are groundbreaking shows. GoTV. Live it, love it.
Akili, 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 akili. Water, water, wash your hands. Scrub with soap, wash your hands. Front and back, wash your hands. To be clean and safe. Wash your hands before you eat your breakfast. Wash your hands before you eat your lunch. Wash your hands before you eat your dinner. Wash your hands before you start to munch. Water, water, wash your hands. Scrub with soap, wash your hands. Front and back, wash your hands to be clean and safe. Wash your hands after using the toilet. Wash your hands after you sneeze or cough. Wash your hands after you touch animals. Wash your hands to wash all the germs off. Water, water, wash your hands. Scrub with soap, wash your hands. Front and back, wash your hands to be clean and safe. Wash your hands before you eat your breakfast, before you eat your lunch, before you eat your dinner, before you start to munch. After using the toilet, after you sneeze or cough, after you touch animals, to wash all the germs off. Wash your hands! Water, water, wash your hands. Scrub with soap, wash your hands. Front and back, wash your hands to be clean and safe.
Yes! Yeah! Yes!
Oh, magical Messi! Takes on 3, takes on 4, beats the goalkeeper.
With over 300 games in 6 weeks, get DSTV to watch the best live football action.
Namibia is known for its beautiful wide open landscapes. However, these deserted spaces also pose numerous educational challenges in our country's rural areas. Because of this, many learners are denied access to proper teaching and learning. At EduVision, we believe that education is the starting point to a journey of endless possibilities.
Soon and very soon, we are going to see e-learning. Soon and very soon, we are going.
The plan for EduVision was to identify areas in Namibia that do not have the proper learning resources, a working school or an education center.
Hallelujah, hallelujah, we are going to see e-learning. No more diet.
My name is Philip Smith. I'm the principal of Exerted Academy in Otjiwarongo. The Project EduVision, the e-learning program, started in 2017. With a project like this, obviously telecommunication, internet connection is a major thing that needs to be sorted out, a logistical challenge. And the fact that we chose Chunkwe Secondary School as the first school didn't make it easier for ourselves. It's very far from Ochivarongo, it's far from Buntu. So the internet connection was a big challenge first of all. So with the help of the telecommunications expert Paratas, they made this dream come true with internet connections via Buntu, Ochivarongo to Chunkwe and then back, the whole process. Like I said, it's interactive whiteboard, so the internet speed, capacity of the connectivity and so forth plays a major role. And so Paratas made this dream come true, and they were on board from the first moment. So very grateful for Paratas.
The project offers teaching assistance of a high standard in science to rural secondary schools within the learner's own community by means of e-learning. This entails the following: live transmissions of lessons from an equipped teacher in a different location to the students in rural areas, students using their own cell phone, tablet or computer to recall each lesson, and interactive lessons as well as the use of a smartboard as a teaching aid.
So if you look ahead at the next 3 years, we get information from the Ministry of Education. The future is very bright. So I think there's a lot of schools who can benefit from this program. Like I mentioned before, finances obviously plays a major role in a project like this. So we're very thankful for all the sponsors that are on board and still on board after almost 3 years of the project. So as long as people from the private sector can get involved, I think we can reach many schools in Namibia, because this project made a good start now. We're already seeing some positive results, and we can just call on all the private sector corporate sponsors to come on board and join in this very, very positive project.
It is EduVision's goal to prepare and guide learners in order to make the modern world they are living in accessible to all.
My name is Magdalena Nyoma. I'm 18 years old and I'm doing my first year at Unam Commando campus, and I completed my grade 12 at Tsumpe Senior Secondary School. I'm doing education, so I'm gonna teach at Tsumpe Secondary School, because there I really need to go there and motivate the learners. EduVision helped me a lot. It assisted us in teaching for mathematics, physical science, and biology. And it also, we get to exchange learning from other schools like Educate, whereby they teach us, and that's the most thing that we benefited from. Studying without EduVision was so challenging. And when EduVision was introduced at our school, things become more easier. The time where EduVision was not introduced, we were so slow in learning. And when EduVision introduced at our school, my learning speed increases. Things were kind of boring. And when EduVision came, my mind changed the way I think. I'm really grateful for what Eduvision gave us. Our class of 2019 was the first group to make it, to perform very well at Tsonkwe Senior Secondary School. So it should keep up the spirit. We need that. It should continue to support us.
Eduvision aspires to ensure that equal opportunity is offered to every learner in rural areas to tap into his or her own potential while working in an environment which views disadvantages not as obstacles but as unique attributes that can be regarded as powerful assets when given the proper opportunity. At Eduvision, we believe that dreams are the foundation of knowledge and hope always triumphs over experience.
No more problems. Everything is proper. Eduvision.
In a corner of southern Africa lies a vast and sparse land, where endless horizons, dramatic scenery, and untouched wilderness abound. (1,500 kilometers of harsh desert coastline, a mosaic of biodiversity, sub-Saharan savanna, acacia bushland, encased by 2 deserts. Home to wildlife and wilderness abundant, yet ever at risk. This is Namibia, home to some of the most noteworthy conservation success stories across the globe. Initiatives forged, manned, and driven by passionate individuals and groups.
People are busy there walking for more than 45 kilometers a day.
Special species and wild locations under constant threat from an increasingly destructive developing world.
One of the world's true survivors.
This is the story of the Namibian wilderness, the stories of the enigmatic wildlife and natural wonders of her realm.
They are not a threat to anyone, if you understand them.
This is the story of those determined to preserve it, and thereby themselves.
I don't think I want to tell my children one day that we had rhinos in Namibia. I want to show them live rhinos.
This is the story of the last defenders.
We have been tracked them for about 7 days, and on the 7th day, we come across the butchers, and there was a shooting. We are not armed. We having a camera and GPS. We are just hiding behind the bushes. If I don't protect this species, who's going to do that? So is that why I sacrificed my life to go on conserve the rhinos.
Armed out in the field with basically a notebook against poachers that are armed with highly dangerous weapons and more. How is this an equal fight?
I started right on the ground as a tracker, and I worked all the way up to be the CEO now, and I know how hard it is. It's commitment and dedication and the patience that you have for the animal. It's really hard. It's like you had something in your house that you are protecting for so long, and when you go away from home, somebody comes and kills you.
Share with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better. We always love to hear from you. Send us your views, comments, and videos with your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
Dedicated to Mother Namibia, the founding father of the Namibian Revolution, Dr. Shafi Kunasem Nyoma, the second former president, Dr. Ifikepunye Pohamba, and the patron of the Namibian National Liberation Veteran Association. The third president, Dr. Hage Geingob, the president of the Republic, and the founder of Harambee Prosperity Plan for Namibia. The first lady, Meme Monica Genkos, and the veterans of the liberation struggle of Namibia, the sons and daughters of the soil. May God bless Namibia.